Hi everyone. We will continue the discussion in chapter 3. So today we are going to begin with the comparison of the Kirchhoff and the Rayleigh-Sommerfeld theorem. So as you might recall, one of the field component of U at the P0 is expressed as an integral of this function integrated over aperture. And remember that P0 is designated by the L01 and L01, and L21 is that the light source. L0 means is our observation point. The L1 is the position at the aperture, and L2 is the light source. Okay. So in generally, you can say that the Kirchhoff theorem, this psi becomes this cosine, and the first Rayleigh-Sommerfeld solution looks like this, and the second Rayleigh-Sommerfeld solution looks like this. And for the case of an infinite distant point source, or you can say that it's the normally incident plane wave, and then we can say that this Kirchhoff theory is given by this simple form. And then we get the cosine theta and the 1 here. Okay, so basically it is integral of a certain function over the aperture. Then we get the field component. What we mean by field component is that the scalar component of either electric field or magnetic field. That means electromagnetic wave. So any component of electromagnetic wave can be expressed in terms of integral at the aperture. Okay, that is the whole thing we have learned, and then it is consistent to the Huygens Fresnel principles. Huygens Fresnel principle is expressed in this way. So UP1 means is that the UP1 is the field component at the aperture, and then it is propagating in the space toward our observation P0. Okay, and then UP0, that means is the field component at our observation point is determined by the field component at the aperture with this phase vector along with this cosine, directional cosine. Okay. So what it means is that at the aperture, each individual point at the P1 has a certain amplitude, and then it propagates as just like a spherical wave. That means in every point at the aperture serves as a point-like source that emit a spherical wave. So basically our diffraction, the field pattern at the P0, which is the result of the diffraction, is nothing but summation of individual spherical wave at that are coming from this aperture. So it is basically diffraction is the nothing but summation of propagating waves. So in other words, it's a kind of interference. Okay, that's what we have learned. So in this case, what we can say is that we have a new terminology, which means we have an impulse response, small h. So we are going to talk about it, impulse response and the transfer function. So impulse response and the transfer function that we are going to discuss in chapter 4. So for the time being, let's assume that our scalar component at our observation point at P0 is expressed in terms of a field component at P1 with this impulse response, P0 and P1. Okay, so it's also impulse response function is it contains the the vector P0 and P1 in terms of R01 and R01. Okay, and along with the theta. Theta is the directional cosine that is making an angle. That is the angle between the vector R0 and R1. Okay. So this is the very simplest form you can think. Okay. And now in section 3.8, what we are going to talk about is the generalization to non-monochromatic wave. In previous case, the wave basically is a function of space and time. And now what we have assumed is that we have assumed the monochromatic wave. That means we have e to the I k dot r minus omega t. And then we have assumed that this is the monochromatic, which is specified the frequency divided by the 2 pi. So that we have assumed this time dependence for the single frequency. Okay, so that was the all the derivation up to 3.7 section. So we have Rayleigh-Sommerfeld and Kirchhoff, and then we have the Huygens integral form for single frequency, or you can say that it's a monochromatic. So it's a single color. So that was the our discussion thus far. And then what we are going to do in this section is that the homogeneous case of non-monochromatic. That means is that there's a additional frequency component. Okay, consider the scalar disturbance. I'm sorry. Here. Consider the scalar difference. The disturbance. Now we have a function of time. Okay, and observed behind the aperture when the disturbance UP1 is instant on that aperture. Okay, so it's both of them are function of time, simply because right now what we have learned is that the monochromatic then all of them UP0t and UP1t, they all have a e to the minus omega t. So basically we already know the solution for the time dependence, but non-monochromatic. We need to find a function of a time. Okay, that is our goal. And let's try to find out how we do it. And basically, the time dependence, we apply once again the Fourier transformation. Okay, for the time dependence, and its reciprocal domain is obviously time versus frequency. Okay, so what we are going to talk about here is that the time function may be expressed in terms of their inverse Fourier transformation, such that the UP1t and UP0t, P0 is once again our observation point, and P1 it was that aperture. Okay, and then they have in terms of a function of t, we have a Fourier transformation in terms of a frequency. Okay. So for the given for the given function of time, we can decompose into the frequency component. Okay. So by the exchange of a variable u prime equal to minus u, we get the this integral form, once again, up1t is given by up1 minus u prime like this. And then what we are going to talk about is that the non-monochromatic time function up1t and up2t may be regarded as a linear combination of a monochromatic time functions of the type represented in the equation 3.10. So that means if we know individual response for this component, so remember that each frequency, and then we know what they are, because if it's given, then we know what they are. Okay. And then we can do the integral for time dependence. The monochromatic elementary functions are various frequencies in U prime. The complex amplitude of the frequency being simply like this. Okay. And then what we are going to do is that using the same the Rayleigh-Sommerfeld equations. Remember that this is nothing but Rayleigh-Sommerfeld equations, but we added the frequency component here, and then remember that this has been changed into k. Remember that this is nothing but this one, and this is what we are going to do is that we are going to plug in. So let me equation 3.51. Okay, here. So here, k is that, remember that k was 2 pi over lambda, and it is nothing but 2 pi c over f, okay, right? So that, in fact, it involves the frequency component, or 2 pi u over c, okay? So in a vacuum. So for the time being, let us assume that we are thinking about light propagation in a vacuum. So what we are going to do is that we are going to look into some of the expression. This is nothing but, we have the k is nothing but the function of a u, which is proportional to nu frequency, so that we get this expression, okay, for each nu. And then what we get here is that once we know this frequency component, then we can find out the time dependent function, okay? Once we know this frequency component, we can find out the temporal dependence by this part, okay? And then this is the most generalization of the non-monochromatic. So if we have a non-monochromatic, that means each of the frequency has a different k, and then for each k we know what the space. So remember that the logic. For each k we have a spatial integral. And for each k, we have assumed a single frequency. Okay, let me just write down. Okay, we have to do the spatial integral. And then for k, we have a nu. and then we do the if we want to find out to get the position of space and time, we have to do the Fourier integral. Of course, we will find later on that spatial integral is in fact is quite related with the spatial Fourier transformation. Okay, so we will see later on. Okay, so that's the logic we are going to follow. So finally, what we have here is that this is our identity is that if you take the derivative, you get this u prime. Okay, so what we have here is that this integral form can be furthermore generalized into this one. Okay, so it's once again is a spatial integral over the aperture in the same form with some kind of directional cosine, but the time dependence is now included for different frequencies by this one. Okay, so this is the most compact expression for the non-monochromatic waves. So the wave disturbance at point P0 is linearly proportional to the time derivative of disturbance at each point P1 on the aperture. So it makes sense because derivative is the disturbance, and disturbance will determine the temporal position, temporal response at the observation point. An understanding of a diffraction of a monochromatic wave can be used directly to synthesize the result for much more general non-monochromatic waves. So basically, what we can say is that once you know the Kirchhoff or Rayleigh-Sommerfeld integral, that form can be readily applicable to non-monochromatic waves. That's the key point. Okay, so today we are going to, in this class, we are going to talk about the temporal dependence on the non-monochromatic wave.